Okay, so drawing the reaction energy diagram of a catalyzed reaction. So I'm not exactly sure how to use the drawing tools in ALEKS because I can't access them from my instructor account, but essentially you're going to need an x-axis for your energy diagram, which is what's called the reaction coordinate. The reaction coordinate basically is the progress of your reaction, and then the y-axis is energy, right? So down the bottom is like no energy, up high is like lots of energy. So if we just draw a line to represent the energy of our reactants and another line to represent the energy of our products, you've used these before in thermodynamics, right? So reactants are down here and then products are up here. This looks to me like it would be an endothermic reaction, right? Because you're going to have to absorb energy to go from the state of reactants to products. So that amount of energy there is going to be my delta H of my reaction, and that is going to be a positive number, so that is going to be endothermic. Anyway, I digress. Um, so that's the straight up energy difference between reactants and products, but the actual path that your reaction might take is something a little bit more like this. Okay, there's a hump in energy right there. So what this hump is representing is your activation energy. So up here somewhere is the actual amount of energy. If I could actually get that to like sit on the line, that'd be great. The actual amount of energy that your reaction requires to proceed. So the activation energy E subscript A. So the actual amount of energy to go from reactants and products is you're going to need to absorb this amount of energy right here to have enough energy for the intermediate transitional state between reactants and products to form. So that's what that would look like for a general endothermic reaction. What a catalyst does is, let's change color. It is going to provide a different pathway between reactants and products. And that different pathway, sorry, my beautiful drawing, is going to have a different activation energy. So that activation energy will be lower. So this is my activation energy for a catalyzed, if I can spell it, reaction. So if you look at the actual energy amount that is required to get over that hump for the catalyzed reaction, it is significantly less for the uncatalyzed reaction. So that is how a catalyst works. If you had a exothermic reaction, it would be the same kind of thing. Of course, your reactants would be at a higher starting level of energy. Oh gosh, I don't want to do that in pink, that's obnoxious. Than your product. So let's just look at a reaction coordinate if our reactants started at a higher energy and our products were at a lower energy. So that would be typically what we'd call an exothermic reaction because of the value of delta H being negative. So right now we have a negative value of delta H, but there is still, so energy is being released, right? Delta H is negative, so that is exothermic. However, you will still have a hump in terms of activation energy. So your pathway is still going to look a little something like this. You're still going to have an activation energy barrier, even though the reaction is exothermic, okay? So if we have a catalyzed reaction, again, you're going to have an alternative pathway with a lower activation energy, comme ci, comme ça, okay? So that will be your catalyzed activation energy. So again, it's going to be less than your uncatalyzed reaction. So the actual amount of energy required to overcome the activation energy, sorry, my bad, will be this amount to go from the reactants to the product. All right, so hopefully that is helpful for you.